Hi, my name is Karina Slater. Today I will be talking about Lab 1. In this lab, I recorded a video of a can rolling at a constant velocity in one direction. I made two position time graphs, one by analyzing the video and another by programming a model where the net force was equal to 0. I then compared the two plots to see if the model matched the real-life data. In the end, the two plots were almost identical, thus making the net force equal to 0 model a good representation of the rolling can. I analyzed the video using Tracker software. I first set the coordinate system with the origin at the center of the can. Those are the purple lines you can see on the screen. The positive x direction is pointing in the direction of the motion of the can, which is to the right. I set the calibration stick to the diameter of the can, which was 7 centimeters. As the can rolled, I set 18 points of mass to track the motion of the can. This produced a time graph, as can be seen in the upper right corner of the screen. I then made a model of the motion of the can using VPython. I set the initial values as shown on the screen. The mass was 0.240 kilograms, which was the weight displayed on the can. The initial position along the x-axis was taken from the start point in the tracker data. The initial velocity was found by dividing the change in position by the change in time. This resulted in a value of 67.759 centimeters per second. I set the net force equal to 0, making the velocity constant. The time interval for this interaction was 0.6006 seconds, which was pulled from the tracker data as well. The new velocity was found using the momentum principle, or Newton's second law, which is displayed in the bottom of the screen. The new position of the can was also found using the momentum principle. This is a screenshot of my model in action. The screenshot shows my can rolling and the position time graph mapping a constant increase in position with time, which corresponds to a constant velocity. When overlaying the graph from the Python model with the graph from the tracker model, the two graphs are almost the same. This shows that the net force equals 0 model is an accurate representation of a can rolling on the floor after the initial push. So what if the origin was set differently? While the position inputs would change, the slope of the position time graph would not change, and the velocity would be exactly the same as the velocity of the original orientation. I'll show you an example. Here you can see I have shifted the origin of the coordinate system to the right. Thus the initial x position of the can is negative. Here are the position time graphs of both the changed and original origin position. As you can see, the graphs are identical except for the numbers along the y-axis, which coordinate to the position of the can. So what does all of this mean? While the net force equals 0 model of the moving can was an accurate portrayal of the motion of the can, this does not mean there are no forces acting on the can. There are actually forces acting on the can, they just cancel each other out. In the diagram below, I have labeled 3 forces and the momentum represented by P of the can. The 3 labeled forces are the normal force, the force of gravity, and friction. The normal force and gravity are equal to each other, leaving only the force of friction to act against the motion of the can. However, in the segment of the video filmed, the force of friction is so negligible that it can be approximated as 0. Thus, the net force is 0. These are only a few of the forces acting on the can. It is almost certain that there are more I have not listed. However, it is impossible to report exactly all the forces acting on the can. It is safe to say, though, that most of these forces are so negligible that they can be ignored and regarded as 0, approximating the net force on the can as 0 in this segment of the video.